Today we're looking at polymers.
Polymers. Word has lost all meaning.
Plastics, latex, rubber, and our favorite polymer, slime.
Oh, yeah.
All on this episode of Science Max Experiments at Large.
Oh, greetings, Science Maximites. My name is Phil, and I think I might have overdone it with the science. I mean, what's a better use of science than creating a whole bunch of slime? Well, I did, and you know what? It's really cool. Slime. I love slime. It always makes me feel like a mad scientist, but I need a good mad scientist laugh. Yeah, it needs work. Anyway, today we're talking about polymers. Polymers like slime. But you see, polymers aren't really a substance. They're more how something is constructed. And there's all kinds of different polymers. There's slime, obviously, and rubber polymers, like rubber. And there's also hard polymers like plastic. Now, polymers are all kind of constructed the same way. Like this. This is a chain. Yeah, so imagine this is a chain of molecules, and all the molecules are the same, and they just repeat in a long line. Now, when you get a polymer like slime, all the chains are not connected or very loosely connected, which means that they can flow over each other like a slime or sort of like a liquid, and they behave like that. So that is slime. But when you get to a rubber polymer, you start to get little bonds in between the chains of polymers that work like this. You see, they still move around a little bit, but they can spread apart, and they become flexible and bouncy. Yeah, I know, a chain doesn't really bounce, but rubber polymers do. Huh? Now, when it gets to a solid polymer like plastic, there's a lot more links, and it's all kind of interconnected, and it doesn't move at all. It doesn't move. Okay, again, harder to tell with a chain, but plastic is very hard and rigid. So let's dive into the world of polymers and make some slime. Yeah, too mad, not enough scientist. I'll keep working on it. Anyway, to make slime, take your white glue and pour in an amount. It really kind of depends on how much slime you want to make. Now, you want to add about twice as much water as that. Yeah, somewhere around there. Great. Now we want to put in just a little bit of soap. Maybe there, that's good. And you want to put in your food coloring. I like green. Green seems like the right slime color to me. It's the right appropriate mad scientist kind of slime. And then you want to start mixing that up till you get the right kind of consistency. That means make sure the glue and the water are equally mixed up. Good. And now we're ready to make it an actual slime by bonding the polymers together by adding liquid starch. Very good. And you want to mix it up.
When you add the liquid starch, it starts to bond the chains of molecules together, changing it from a liquid to a slime.
It's coming along. And there you go, slime. Now, if you want clear slime and not opaque slime, you want to use clear glue and not white glue. But that's basically the recipe. So there you go, slime. Too supervillain? Yeah, okay, well, anyway, all right. Now all you need is an expert to help me max it out. Of course, my interface is hand gesture based, so I don't know if the slime... Oh, hey, there we go. Great, so you get it. Oh, of course, Sarah from Mad Science. Mad Science, they really know their slime. This is great. Okay, I got it. Close. There we go. All right. Ugh. I'm not sure bringing it through the portal is such a good idea, but at least I'll have it on the other side. Ugh. I have a pot. Why do I have a pot? I didn't have a pot when I went through the portal. Is someone somewhere missing a pot, or did it just create this pot out of nothing? Huh. Hey, Sarah!
Hi, how are you doing?
Good, Sarah from Mad Science, you're gonna help me make some slime.
Yes, I actually brought some... Oh, this isn't slime, this is a pot lid.
Hey.
Oh,
Well, at least we have a set. Doesn't answer any questions, though. And I guess we're gonna have to make some more slime.
Definitely. What kind of slime do you want to make?
What do you mean, what kind? Is there more than one kind?
Oh yeah, there are tons of different kinds of slime with lots of different ingredients and recipes.
Oh, I only know the one. Can you show me all the others?
Of course, let's go make some right now.
Okay, great.
Awesome.
Come on down to Sal's Science Shop and see me, Sal, while you shop for science. This week only, Sal's one-of-a-kind, once-a-year polymer sale. 50 to 75% off anything made of polymers. Rubber? That's a polymer. Polystyrene. When you're eating your next meal, I recommend some polypropylene. Low-density polyethylene. High-density polyethylene. You want some polytetrafluoroethylene? We got it. We've even got polychlorotrifluoroethylene. Do they even know how good a deal this is? Because you're not gonna find that kind of deal just like every day. But hold the phone. Polymers aren't just plastics. Rayon, nylon, Teflon, you name the lawn, we got it on sale. What do we want? Polymers. When do we want them? Anytime during normal business hours. Wool, silk, even cotton. Polymers, polymers, polymers. Polymers, polymers, polymers. Word has lost all meaning. Glue, paint, umbrella fabric, oh yeah. Carpet, you bet that's on sale. Roberta, I'm running out of sale signs. Buy it and I'll put it in a plastic bag, also made of polymers. Seriously, Roberta, we can't have a sale on everything. Oh, hey, even you, even me, the proteins in our bodies, even our DNA, all polymers. So come on down to Sal's Science Shop and get a great deal on your polymers for a limited time. I mean, it'd have to be a limited time, right, Roberta? Because, I mean, I can't discount everything in the store to 75% off. How am I gonna make any money? I mean, are we still rolling? 100 different kinds of slime.
Yes, it's gonna be so much fun, but we're not gonna make 100 today.
Yeah, I know. We're just gonna do our top favorites.
Yeah, it's gonna be super great.
All right, what are we starting with?
So our first slime we're starting with today is some really cool molding slime. Now this slime, actually, if you leave it out overnight, it'll harden and you can make an imprint of whatever you like. So here, we made an imprint of our little tool there. So we're gonna look at a little bit more liquidy slime, starting with this one over here, which I believe you already know about.
This is cornstarch mud.
Exactly.
You hold this.
Sounds
I'm gonna
good.
hold this and we're gonna try pouring it. Whoa, oh,
Whoa.
so, see, it's like a liquid, but then if you do it fast, it's like a solid. All right, what's next?
Over here, we have some other really awesome types of slime. So right over here, we have some crunchy slime.
Crunchy slime?
Exactly.
Why is it crunchy?
Now it's crunchy because we've actually added a few beads inside of it to make it crunchy. So this is some really cool, awesome slime.
Here, you take half.
And you can feel the beads as you stretch it out. It's so cool.
This one is a little harder to clean.
Exactly.
I'll just do that. All right, so what's next?
So next we have some really cool glow-in-the-dark slime.
Glow-in-the-dark slime?
Yeah, it's so awesome.
Ooh, look at how much it glows. That glows a lot. That's super glowy slime. So to do the different kinds of slime, we need the polymer.
Yes.
And then the thing that sticks the polymers together.
Exactly.
So the glue is the polymer.
Glue is the polymer.
And the starch is the thing that bonds it.
Yes.
Uh-huh.
Very cool.
And then you put the thing in that makes it the kind of slime.
Yes, right before you add the bonding component, because if we keep adding stuff after it's already made, it unfortunately won't be able to take it. So we add our powder before we add our starch in this situation.
Should we go on to the next thing?
Yeah, let's move on to
More slime! Plastic is great, and plastic is everywhere. But the problem with plastic is it isn't very biodegradable. It doesn't break down in the environment. I'm still on hold. Oh, well. There you go. Back for another couple years, I guess. But here's a way that you can make bioplastic. It's fully biodegradable because it's made of natural materials.
The recipe is easy. 2 parts cornstarch, 3 parts water, a few drops of cooking oil, and some food coloring to make it whatever color you want.
Purple, science purple.
Mix it up and it turns into a paste.
Now what you'll need are 2 things. 1, an adult, and 2, a microwave.
Put it in for 30 seconds.
Clock wipe. There we go.
Then take it out and mix it some more until it cools down. Then you can pull it out and use your hands to sculpt it into a shape or take the shape of something else.
Once you put it all the way around, you can turn it into a little flower pot.
Once you've sculpted it,
You need to wait for it to dry, which will take about a day. Clock wipe.
after waiting a day,
Huh? What? It's been a day? Oh.
you have something made out of bioplastic. Like this little flower pot you can use to grow a small plant.
And then when it grows big enough, you can take this biodegradable flower pot and plant it right outside in the dirt, and this pot will biodegrade and turn back into dirt. Pretty cool, right? Well, let's max it out. Biodegradable Frisbee! Check it out! It's a Frisbee, but it's biodegradable. So you throw it around in the park, but if you lose it, it turns back into dirt. Ha-ha! What, not enough? Okay, clock wipe! Biodegradable lawn chair! Use it for one season and then return it to the earth afterwards. I think this is one of my best Science Max. Okay, bioplastic lawn chair, not as strong as regular lawn chair. We've learned that lesson now, so that's good to know. I mean, how would I have known if I hadn't tried it?
Sarah and I are looking at different recipes for slime.
All right, what do we got here?
So over here we have some amazing foamy slime, which has so many ingredients in it. Here, watch what happens when we start pulling it out.
Ooh, wow. So it's like,
Super stretchy and super fluffy.
here, that's great. Okay, now you gotta hold yours. You gotta hold this end. Okay, you take, and then take some more. And then we take that. And then, yeah. It gets thinner and thinner and it becomes more and more lines of foamy slime.
Yeah. And the last kind of slime we made today is some classic flubber slime.
Ooh.
So much fun.
Now, why do you think it's called, is it flubber slime? Because is it really a slime?
It is a slime, yeah. It's super fun and it's super stretchy.
Oh, okay, I get it. Look at that. And it's sort of like a little bit like gelatin.
It is almost like gelatin.
Here, you can have some. There you go. Whoa. Ah, whoa. All right, so Sarah, now what we need to decide is how we're gonna max it out.
Right.
Like, should we just get a lot of slime?
That sounds like a really good idea, but we are gonna need something to put it in because we can't just have slime all over the floor.
Okay, you're right. So we'll get some sort of container thing.
Yeah.
And we'll see how much slime we can make, and then we'll just play with it and see what happens.
Sounds good.
And yeah, we will experiment because it's science.
Yeah.
Okay, high five. Careful high five so we don't splatter. Okay, good. Okay, let's go. This is right.
This is a rubber glove. Well, actually, it's a latex glove. What's the difference? I will get to that in a second, but I'm sure you can agree it's super stretchy. How stretchy? Let's fill a rubber glove with water and see how big it gets. So, difference between latex and rubber. Well, it all comes from a rubber tree. Well, actually, it's a fake tree. It's just to show you how it works. The sap of the rubber tree is collected just like this. There's a spigot, and then the sap goes out, and it's collected. It's the same way that the sap for maple syrup is collected. And this is natural latex. If it's dried out, it becomes natural rubber. Latex generally means the liquid form, and rubber means the solid form. But wait, then why is this a latex glove? The glove is not liquid. What's the deal? Well, generally, latex means water-based or liquid, like latex paint. But it could also mean synthetic latex. That's latex that's man-made and doesn't come from a rubber tree. So, we call rubber gloves because they used to come from rubber trees, but now they're usually made out of man-made latex. But either way, they're super stretchy. I wonder how big this is gonna get. Science! Sarah and I are maxing out polymer slime. How?
Maxed out tub of slime! Whoa! Okay, so how do you feel? Are we mixed up enough?
First, we mix up a bunch of slime in a garbage bin.
So with the polymer chemistry, the polymer is generally a liquid, right?
Yep.
And the bonding agent makes it stick together. So the more we use, the more of a solid we get.
Exactly, yeah.
So we want to split it and make it sort of halfway between a liquid and a solid, and I think we're exactly at the right stage.
It looks perfect.
Oh, yeah. Okay, so let's dump this garbage can in.
All right.
All right. Then we dump it in.
Oh, gross.
Turns out we needed more slime.
I don't think that's gonna be enough.
I think we may need some more slime.
Yeah, how much more do you think we need?
So we added 11 more.
Ah, delicious.
Perfect.
Last one. Oh, yeah.
Then we experimented.
Oh, yeah. We have a giant tub of slime.
Because the slime is stretchy, it created amazing bubbles.
So do you think I could blow a bubble with the slime?
Well, maybe not you, but definitely
wanna
the air
try this?
compressor.
No, no, I'd have to just put it on my face. I think I've already got it on my face. Then there was only one thing left to do.
We get in the slime.
Can we do that?
We can totally do that. This is Science Max.
That's so exciting!
Going swimming in slime.
Yes!
Who's going first?
You are!
I am, obviously. All right, this is how Science Max does polymers. 3, 2, 1. Plastic is everywhere, but what can we do with it aside from recycle it? Well, we can reuse it to make cool plastic charms. But you're gonna need the right kind of plastic, and you need polystyrene. Just look for the little number 6 inside the recycle symbol.
Cut out some plastic and decorate it however you want.
There we go. Haha, check it out. The Science Max logo. Also, I've made a couple other things. I've got a chemical symbol, an atom, and this is me in some slime.
Then get an adult to help you put it in the oven or
Toaster oven.
at 350 degrees. It only takes a few seconds for the plastic to shrink to 1/3 its size.
The reason why this happens is when plastic is manufactured, it's heated and stretched out and then cooled, and it sort of freezes in that stretched out shape. And when you reheat it, it shrinks back down to the unstretched shape.
Get your adult to take it out and wait for it to cool, and you'll have yourself some small plastic designs you can use for keychains, bracelets, name tags, bookmarks, whatever you want, all using the power of polymers.
Awesome. I'm gonna make all of those. What was that again? Keychain, ornament, magnet.
Magnetic putty in 60 seconds.
This is magnetic putty.
Thank you.
This is magnetic putty.
10 take.
This is magnetic putty.
26.
This is magnetic putty.
2,635.
This is magnetic putty.
I can't count this high.
This is magnetic putty. Magnetic. Oh, it's not a magnet. It's attracted to magnets. Oh, that makes more sense. This is magnetic putty, and this is a magnet. The putty is made of polymers, which means it can flow over itself. It also has lots of iron filings in it, which is why it's attracted to magnets.
This is what happens over several minutes.
And there you go, magnetic putty.
Okay, so where were we? Oh, yeah.
3, 2, 1, yeah!
And remember, don't try this at home.
Slime!
Sarah and I enjoyed our maxed out tub of slime. So let's recap. Slime is made of polymers. Polymers come in a lot of different forms. It's all about long chains of molecules. And none are more fun to swim in than slime.
Do I have slime here?
Ooh, yeah, definitely.
Slime here! Slime! Slime! Yeah! High fives! Yeah! Slimy high five! Yeah!
Today on Science Max, it's all about the power of water. I'll see you later. We filter it, pump it, paint with it, and most importantly, use it to crush stuff.
Oh, crushing!
All on this episode of Science Max, Experiments at Large.
Ha! Greetings, Science Maximites. My name is Phil, and this is Science Max Experiments at Large, and this is a syringe. You might know syringes from when you get a needle at the doctor, but syringes are used all the time in science because they let you measure very precise amounts of fluid. Now check it out. You push the plunger down, and it comes out the top. Or you could pull the plunger in, and it would suck more fluid in this way. But check this out. I've got a syringe attached to a hose here, and this hose is filled with water. And I wondered if the hose was really, really long, how hard would it be to push this plunger down? Of course, I don't know where the end of the hose is because it was really long and I had to string it all the way around, so, here it is. Okay, so let's find out. Push the syringe down and water will come out the other end of the hose. Pretty cool. You see, this is called hydraulics. Hydraulics is a branch of science that deals with fluids like water. But hydraulics are also a mechanism used in a lot of machines. Check this out. This is a syringe with a short hose on it, much shorter this time. And I press down on the plunger of the syringe and water comes out. And I pull in on the syringe and water goes back in. Because the plunger is airtight, it allows me to push or pull the water. But what if I close the system and take another syringe and attach it to the end of the hose like this? Well, then, if I push this plunger in, this syringe fills up with water. And then I pull this plunger out, the syringe empties. So check it out. This plunger raises and lowers based on what I'm doing with this plunger. And you know what that means? We've made a remote control. Huh? Check it out. So, if you take two syringes and you take a hose and you attach them to something you want to remote control, voila, you can build something like this. We have made our very own robotic arm that you can power remotely with hydraulics. Pretty cool, right? If you want to build one of these yourself, here are the materials you need. First, you need two supports and the arm. I used pieces of wood, but you can use wooden spoons, rulers, or pencils. You'll need some craft sticks, elastics, and a paper plate. And of course, two syringes and a hose, which you can get in an art supply store or a hardware store. Here's how you build your own hydraulically powered arm. First, make the base by tracing holes for your supports the width of a craft stick apart. Cut out the holes and use a craft stick and elastic to secure the supports underneath the plate and on top. Then add some elastics and a piece of craft stick in the middle so the supports won't scrunch together. Because we are holding this whole thing together with elastics. Then get your syringe in there and keep it propped up with more elastics. Then get your arm and slot it in between the supports. The arm should be horizontal when the syringe is half full. Elastics to attach the arm and the syringe. Then push down on this end of the plunger and, ha-ha, you have a remote-controlled robotic arm. You can also max it out even more by adding more degrees of movement. You can make the arm rotate side to side. You can even add a little claw attachment at the end and power it all using syringes. Haha, science and hydraulics. So let's max it out. I just need an expert to help me. Let's see. And over and that way. Chris from Logix Academy, of course. Logix Academy knows all about building robot stuff. I'm sure Chris can totally help me. Let's go.
Oh, hey, Phil.
Oh, hey, Chris from Logix Academy. Great to see you.
What took you so long?
How long was I gone?
And what's with the orange lab coat?
Oh, it happened again. It keeps changing the color of my lab coat. But this time, Chris, I prepared for it, and I wore another lab coat. See?
Blue?
No! Well, you know what? This is happening a lot, Chris. So I wore another lab coat under this lab coat. I'm gonna have to wear a lot of lab coats, though, because this is happening all the time. We should talk about hydraulics, right?
Okay, yes,
yeah, because we
yes.
got some cool stuff planned. Okay, so we're just gonna get the table in here. Whoa, okay. This is the hydraulic arm. Check it out.
Oh, very cool, very cool.
If we want to max it out, What can we do? We could make it bigger, we can make
What
an
if we did
arm.
it so that the force you put on this side gets multiplied so that this side's even stronger?
Ooh, what do you call that when that happens?
Force multiplier.
A force, I like that. Force multiplier, it sounds like a video game. So we would have a lot more power.
You have a lot more power, which we could do fun stuff.
Yeah, so if we had like lots of power, what would we do? We'd like crush something.
Yeah, let's crush some stuff.
Yeah, we could crush some stuff. Okay, can we start with syringes though?
Yep.
And then we'll work up as we go.
I like it.
So what do we need? Do we need different sizes?
So yeah, I was thinking we need a small
A delicious plate of cheese and crackers, my favorite snack. But these crackers are pretty salty, so I should probably pour myself a glass of water first, huh? No, my cheese and crackers! Why? Why does this happen? Why does the water stick to the glass? Well, because of science. And the reason why it happens gets a little complicated, but it boils down to this one simple thing. Water likes to stick to things. Huh? Did you see? Did you see how it stuck? No, of course you didn't. You know why? Because it only sticks on a small scale. See those drops of water? That's water sticking to the surface. But it only works when the surface tension of the water is less than the force of gravity, which is why water drops fall when they get bigger. So it sticks to things. That still doesn't explain why you can pour water out of some containers without any drips, and other containers make it nearly impossible. It's all about the angle. Water will flow very easily when there isn't a large change in direction, like around the curved top of this glass. But when there's a big change in direction, like at the mouth of this teapot, the water can't make that turn as easily. This is also why pouring from a full glass is much messier than one that's less full. Pouring out of a full glass, the water only needs to change direction this much to flow down the side. But from a half-full glass, the water would need to change direction this much. So all this happens because water likes to stick to things. So let's do an experiment and coat this glass with hydrophobic spray. Now, hydrophobic coatings repel water. So if it's repelling the water from the outside of the glass, will we still have the same problem? Well, let's find out. Hydrophobic coated glass, non-hydrophobic coated glass, or just regular glass. Water likes to stick to surfaces, but it can't stick to one coated in hydrophobic coating. That's impressive. Should we try something else? Well, that's one way to solve the dribbling glass problem. Except you can't coat your glasses at home with hydrophobic coating because it's not good to eat. The secret is using a container that has a very sharp angle between where you're pouring the water and the underside of the glass, like this jug. And there you go. Now I can enjoy a nice glass of water with my cheese and crackers. Oh, right, wait, hold on, I will remake the crackers into, see, look, see, it's fine. It's fine, I'm not really gonna eat that, I'm just kidding. Chris and I are maxing out our hydraulic crusher.
Yes, before we get to that, I have a little game I want to play.
Okay, great.
Okay. You can pick either the small one
The big
or
one!
Okay.
So what's the game?
Simple thumb war. I'm gonna press down on this side, you press down on that side, we'll see who wins.
Okay, are you ready?
Yeah.
1, 2, 3, go! Oh, wow, that was really tough. Why was that so hard?
Well, Phil, I'm just really strong.
Wait a minute. My turn. Okay, 1, 2, 3, go! Yeah! See, pushing down on this one is way easier. You wouldn't think that the small syringe would be easier. Why is that?
The reason for it is that you have to push this one down a lot farther than you have to push this one down.
let's see.
See how
Oh,
far
yeah.
this one goes, and this one's barely
This one
moving?
travels much more. This is how we can exchange a little bit of force over a long distance.
That's right.
To a little bit of distance at a lot of force.
That's exactly right.
Just like the lever, it's a mechanical advantage. But in this case, it's hydraulic advantage.
That's right.
Chris and I push down on small syringes, which gives us more force on our larger syringes. Our crusher was ready to go.
Ooh, how about an orange? 1, 2, 3.
We squeezed down and... Then we tried a walnut.
Are you allergic to nuts?
I am not.
1, 2, 3.
When we tried a golf ball, we reached the limit of what our plastic syringes and our hands could do.
We need to come up with a stronger, more awesome crushing machine using hydraulics.
That's right. I have some ideas.
Okay, good. We can use metal.
We can use metal.
And we can
we can go bigger as well.
Ew, this water is gross, but I'm gonna drink this water. Why? Well, because of science. No, but I'm not gonna drink the water like this. First, I'm gonna use the power of science to help me clean it. How? By using gravel. Gravel, yes, gravel. So, say I've got some dirty water, and there are particles floating in that water. Large particles, your rocks, your wood. These styrofoam bits will act as the large particles. You pour it into the gravel, and the large particles get filtered out. See? Nothing but clean, clean water. Yeah, I know what you're thinking, Phil, that's not really clean yet. That's because we haven't done step 2, sand. Sand? Yes, sand. Let's say that these plastic beads are small particles. That filters out the tinier stuff. There, huh? Clean, right? No, it's not very clean. So, we filter the water in the next step with charcoal. What? Charcoal? Yes, charcoal.
Charcoal works just like gravel and sand, except on a microscopic scale. Say these bits are tiny particles you can't even see. The charcoal catches these like the sand and gravel caught the larger particles. This is called a
Gravel, sand, and charcoal filter.
The gravel catches the big particles, the sand the smaller ones, and the charcoal the microscopic ones. These kinds of filters are used all over the world to clean drinking water.
Delicious. Science.
Max Historica.
This is Archimedes.
What? Who said that?
It's me, the narrator. We're doing a segment.
Oh, well, I was working. Don't sneak up on a guy like that.
This is Archimedes, an ancient inventor and one of the greatest scientific minds ever. One of his famous inventions was the Archimedes screw, which was used to make holes in wood.
No, that's not what it's for. It's for water.
Right, used to make holes in water.
What? No! Look, did you even do your homework?
Hold on, it's here somewhere.
Look, I'll just show you. You see, in ancient times, we had many uses for something that could lift water up. From a well, or to take lake water from the lake and put it into a farmer's field, and that sort of thing.
Okay, I've got it from here. So, Archimedes invented a screw, and he drilled a hole in the side of that container.
No. Look, just sit down. I'll explain it, okay?
I am sitting. I'm in a voiceover booth.
Good for you. Now be quiet. Now look. What you do is you put the screw in the water like this, and then you want to raise the water higher, you see? And so turn it around like so, and the water fills each gap in the screw, and it starts to come up. It gets to the top, and look at this. Look, we've got water coming at the top there. The water is being pumped up. It is the first water pump.
I see. Still seems like a lot of work to fill a glass, but it's very cute.
No, we made them bigger. We obviously were not going to make them this big. This is not very useful.
Right. Archimedes, one of the greatest scientific minds ever. Chris and I are maxing out a hydraulic crushing machine. We tried one out of plastic, but now it's time to make one out of metal. These are called hydraulic cylinders, and they work the same as our syringes. Small ones on this side with a lot of travel, and then a larger one on this side to multiply the force. And some mechanical advantage with a lever to help us push even harder. We tried crushing a watermelon, and it worked great.
So what else do you want to crush?
We crushed a coconut,
It's cracking. Oh, there we go. Oh, it's gonna leak.
and then a can of pop.
Science Max Cola, now in the new smaller can.
Let's really challenge this press. Perfect.
A piece of wood.
We tried to crush the wood, but we weren't able to get it to budge. So it's time to max it out even more.
I think we're gonna need like a multi-story industrial-sized hydraulic press.
You know where we can get one of those?
I do.
Awesome. This is water. Things float on water, like pool noodles and wood and toy boats. And now we're gonna do an experiment with how paint floats on water.
How's this supposed to work again?
Oh! I'm supposed to take the paint out of the can first. This is a fun experiment you can do at home. All you need is a container, some water, and paint. But not just any paint, special paint you use for hydro dipping. That's hydro, meaning water, and dipping, meaning dipping.
Carefully pour the paint on the water and add a few different colors. Then take a stick to swirl it up into a pattern.
Then you get something you want to paint, and you carefully put it in like so. But don't pull it out as soon as you get it in. You have to spread the paint away because it'll stick when you bring it back out. And then when you pull it out, whoa! Hydro dip. Let that dry, and then you have a very cool painted toy. Let's do some other stuff. This is a bike helmet.
If you put tape on what you're painting, you can remove it later to make parts that aren't painted.
Skateboard. Whoa! Oh, that's pretty cool. Now to max it out. Hydro dip pants.
Wearing the pants when you do this is super messy and not something you should try at home. But the results weren't bad.
Science pants! Science pants! Science pants. One of the ways you can experience the power of water is watching it wash away dirt. You can experiment with this yourself by making your own erosion table.
To make your own, fill a plastic tub with sand and tilt it up. Cut a hole in the tub at the low end and put a hose with a trickle of water at the high end. Then to complete your model, fill it with
A little happy town.
this small model shows how rivers cut their course to the ocean by following the lowest point. Try to design your town and the layout of the ground so the river goes around the buildings.
I'll see you later. I'm gonna take a swim in the river now.
There are lots of ways to experiment. Change the amount of water, or the steepness of the angle,
Look at the soil, it's all getting eroded over here.
or the way the town is laid out.
Every time you do it, the river goes in a different direction,
And have fun.
Oh, phew, I'm tired. I'm just gonna lie down.
and that is the power of water.
Chris and I are maxing out a hydraulic crushing machine.
What about this? Is this what we're gonna use?
We went to the Natural Resource Canada's CanMet Materials Laboratory, which is a federal research lab.
Oh, this is good. Oh, look at that! Oh, is this what we're using?
No.
Oh, I can use this. Hold on, let me figure this out.
Maybe later.
Really?
It's just over here.
CMAT is the largest research center in Canada dedicated to metals and materials research.
This is it.
Oh,
This is it.
yeah, right! Hydraulic press. How much force does this apply?
This can do 2 million pounds,
That's over 900,000 kilograms.
which is about 20 cars.
Let's crush some stuff! Oh, crushing! We gotta get the stuff. Okay.
We started out with the piece of wood which defeated our last press.
And go!
That sound.
Awesome. Reversing.
It turned our wood into a pancake.
Whoa, totally flathead.
So it was time to try some other stuff. We crushed a ball of plasticine.
That is neat. You sort of made a rainbow.
Yeah.
Aluminum foil.
Aluminum foil.
Yes, it is now a solid plate of aluminum.
And a basketball.
Basketball. Good thing we got these earplugs in because when it pops, it'll be loud.
What?
Never mind.
This hydraulic press was so maxed out, we had to think of the toughest stuff to crush. We crushed hockey pucks, a safe, we crushed a hydraulic jack with the hydraulic press.
This is a metal vise. Hard, strong,
Yeah, it's steel.
heavy steel.
Whoa, look at it bend. Wow.
Now it's time to crush a bowling ball.
It totally exploded. Science Max, experiments at large, hydraulics. Whoa, nicely done.
So fun.
I should reverse it and we should start cleaning all that stuff up,
Yeah,
huh?
I think so.
Okay, reverse. Stable structures are what we're building on this episode. Bridges, cups, pencils, blocks, boxes. They're all being built up and falling down. Plus, how stable can you make a structure using fruit as the base? Stay tuned to find out on this episode of Science Max Experiments at Large. Greetings, Science Maximites. Get your hard hats out because today we're gonna be building things. Like I always say, what's the point of science if you can't use it to build cool stuff? And today's episode is called Stable Structures. Now, stables are the buildings where horses sleep. So, stable structures means... I think I have the wrong kind of stable. Today, we are going to be building a gumdrop dome. And gumdrops are already kind of dome-shaped, but they don't hold a lot of weight. Yeah, can't hold much weight. But you can make it hold a lot of weight if you build a geodesic dome. A geodesic dome means a round shape made out of straight lines, and that's what I've made here. All I used is gumdrops and toothpicks. It's very easy to make, and I'll show you how to do it. First, you need to start with a pentagon, a 5-sided figure. 1, 2, 3, 4, 5. And then stick them all together, obviously with toothpicks. Then what you want to do is you want to start making triangles. So you stick a toothpick in here and a toothpick in here, and then you put a gumdrop at the top of this triangle, just like this. And then you make another triangle here, and here, and here, and it becomes a whole bunch of triangles, you see? Easy to make as long as you start with a pentagon on the bottom. Now, once you've built one, I suggest you build 2 more, because then you will have a stable base and you can see just how much weight these hold. Yeah. You wanna max it out? Oh, okay. Let's max it out. Oh, a little collapsing, but still not bad for gumdrops, right? So there you go, the geodesic dome. That's what you research if you want to learn how to build one of these for yourself. But now, let's max this out even more. Okay, now I just need an expert to help me out. Do you like my new interface? It's good, right? Watch this. Oh, wait a minute. That's not, okay. Wait, no, that's not the right gesture for that. It's all gesture-based, so I gotta, this? Nope. This? Nope. That? Ooh, okay. Expert. I want experts. Oh, okay. It's voice activated. Great. Sarah from Mad Science. She'd be perfect for this. Good. Close. I can leave it running. Sarah?
Hey, Phil. Back here.
Hey, Sarah. Sarah from Mad Science. Great to see you.
Thank you. Great to be here. I like your lab coat. It's a really nice color.
Wait a minute. It's supposed to be yellow. It must have changed to orange in the portal. That's okay because this is not the first time that's happened, so I've installed a little secret thing on the app that allowed me to get a new one from storage.
Oh,
Watch
perfect.
this. Huh. Didn't work. Oh well, I'll get another one later. All right. Anyway, we are going to max out the geodesic dome.
Amazing. That's so cool.
Yeah, so we just want to make it bigger. So how do we do that?
Okay, well, there's a couple ways we could do that. We could add a few more points of connection, change the shape of it, make it a little more complex so it's a little bit bigger. Or we can use the design right now and use different materials to make it bigger.
Okay. Well, you know what? I think we should do both of those things. I think we should make it more complex and bigger, but why don't we start with bigger?
Okay.
But we'll use the simple design right here, and we'll just get like long wooden poles instead of toothpicks.
Perfect, yeah. And then, what will we use for the gumdrop?
I guess we can't get big gumdrops, huh?
No, I don't think so.
What about oranges?
Huh?
Yeah, oranges could work.
Maybe, yeah, because
Yeah.
you could stick the poles in and then the oranges would be, okay.
Yeah, that's
We'll go to the Science Max Fruit Market and we'll get some oranges.
Perfect.
And I'll get a yellow lab coat. I don't know why that didn't work. Is this a maxed out number of oranges?
I think so.
Or is it just a mediumed out number? We don't really need many more oranges than this.
No.
So, there we go. So we got our oranges. Those are going to be our gumdrops, and
These wooden dowels will be our toothpicks.
we just have to start with a pentagon, right?
Yes.
5 sides. So why don't we just lay that out and see what it looks like here.
We start building this dome the same as the gumdrop dome.
So, like this.
We stick the dowels into the oranges to make our 5-sided pentagon.
Good, like that.
And then we go up from there by making a few triangles and sticking the oranges on the tops.
Oh.
But because the oranges are heavy, the triangles are pretty wobbly. That is, until we get them all connected with cross pieces.
Yeah.
After that, it seems to hold up pretty well.
Okay, let's see if it holds it up. Whoa! That's exciting. That is very exciting. Let's do the same thing. So you make a triangle here, I'll make a triangle there, and then we'll connect them.
Sounds good.
2 layers, orange dome. I'm pretty excited about this. This is nice.
I'm surprised that the oranges actually hold it together because
Oranges aren't really that strong.
No, exactly. But the structure itself is really strong based on the design of it.
Yeah, because it's all about the shapes, right?
Exactly. And we're using lots of triangles today, which are one of the strongest shapes on Earth.
Ooh, strong. Well, then making something out of a lot of triangles makes it really strong.
Exactly.
Yeah, okay, so let's make that top layer of
All right.
things. We only need one more orange.
Yeah.
This will be the one, top layer.
Right in the middle.
one orange on top with 5 dowels from each point and
Yeah! Orange juice high five.
in fact, it worked so well, there's only one thing left to do.
Is there a way that we can maybe max it out even more?
Watermelon? Watermelon. We could get the round watermelons. You ever
Yeah.
seen those? They're like the size of a bowling ball or
Yeah.
smaller, a little bit smaller.
That's perfect. And they're nice and full inside, so they should be able to hold the posts into place.
Okay, we'll try one more time with watermelon. Inside dome high five. Yeah! You may have heard of cup stacking, and if not, you're missing out because not only is it fun, but it's something that kids are the world record holders at. And it's all about, you guessed it, stacking cups. Now, I have learned the pattern, but I'm not super fast at it. The world record is actually 4 seconds, and this is what that looks like. But you can't use camera tricks to help you. You have to practice to get faster. Now, you don't need to use official sports stacking cups, but if you don't know your science, some things will work against you. First of all, these cups have holes in the bottom, which makes them not very good as, cups. Why do they have holes in the bottom? Because of science. You see, when you pull the cups apart, there is air that needs to get inside this cup. If you don't have a hole, like these ones, the air makes them stick together because there's nowhere for the air to get in except for underneath, and they will stick. Once again, let's compare. Also, you want the cups to have some weight because if they have some weight, they'll fall out of each other easily. If they don't have any weight, like, say, these styrofoam cups, it becomes very difficult. And cup stacking with trash cans. Okay, here we go.
Even though these trash cans were heavy, they didn't have holes in the bottom, which means they stuck together. A lot. So why didn't I drill holes in the bottom of these trash cans?
Okay, and then
Well, I needed them in episode 6 to make 11 barrels of slime.
okay. 2.
But I eventually did it.
And time. Okay, There you go. The world record in trash can stacking. I know it doesn't seem very fast, but first of all, that was hard. And second of all, I am the only one to do it. So therefore, I hold the record.
Sarah and I have already made a great dome out of oranges. Now we're maxing it out even more, but this time using
Watermelon!
Watermelons! But not the giant watermelons,
Nope.
the perfect spherical watermelons. They'll have to do pretty good to be better than the oranges.
Definitely.
All right, so we just do it the same way?
Same way.
All right.
Let's do it.
I'm sure I'm not telling you something you don't know when I say watermelons aren't great for building structures with.
Super wobbly.
But the fact that we can make a structure using watermelons just proves how amazingly strong a geodesic dome really is.
Have we done it?
Yeah.
We've done it! Yeah, watermelon dome!
All right, we've got our gumdrop dome,
We've got our orange dome!
and we've got our
Watermelon dome! These are awesome maxed out domes. What do we want to do to max it out even further?
I think the watermelons were a little too heavy. Maybe we should go back to something lighter.
So we can make it out of gumdrops, which will be like more complex.
Exactly.
And we won't get orange juice raining on our heads all day,
Yep.
which is what happens with this one.
Max Historica. This is Leonardo da Vinci,
Ciao.
one of the greatest inventors to ever live. And this is a pile of wood. One of the greatest piles of wood to ever be piled. Now, Leonardo is going to construct a bridge out of this wood. This is Leonardo's hammer. One of the worst hammers in the history of hammers. Now Leonardo must construct his bridge using no tools at all. No, that hasn't been invented yet. How will Leonardo construct a bridge using no tools at all? Well, he is one of the greatest scientific minds. One of the greatest scientific minds in history. Oh, each piece of wood is supported by another. And that's what's known as Leonardo da Vinci's self-supporting bridge. Leonardo's done it. But there is a flaw in the bridge. It's very strong when you apply downward force, but not so strong when you push on it sideways. Fortunately, Leonardo can devote his great mind to figuring out how to clean up his workshop. Haha! Join me, one of the greatest narrators in the history of narration, next time on more Max Historica. Let's recap. Sarah and I have maxed out our simple geodesic dome, but now it's time to make it even more maxed out. We need to increase how complex our structure is.
So right over here, we actually have a dome that's just made out of triangles.
Ooh, look it. It's nothing but there's triangle there, there's a triangle there, triangle there, triangle. So all triangles.
All triangles. And see how much bigger it is even compared to our first one?
Yeah.
And that's just by adding more points. Over here, we have one that uses pentagons and triangles.
Ooh, let me see. Okay, so we got, oh, there's a pentagon there.
Yep.
There's a pentagon there. And then we got triangles here.
Yep.
Can we go bigger than this? Because this is good, but this is not maxed out enough.
Sarah had the idea of lengthening the poles
Shish kebab skewers, I love those. I use those all the time in my science experiments.
and making a bunch of pieces that fit together.
So we just make a whole bunch more of these.
Yep.
And then we'll make some sort of big dome.
This is awesome! So we maxed it out, and it worked great. But gumdrops started to become a little hard to work with.
Every time I do one attachment, another one comes apart. So I had to get inside to hold it up with my head.
I think I've got an idea.
Oh, yeah?
Be right back. Yeah.
Okay, but should I get out or should I? It's okay, I can stay in. I can just keep fixing while it's collapsing a bit, but it's okay. Wait, this is inside. No, this is outside. Wait, hold on. Help, Sarah?
Hey, oh, my.
It kind of collapsed a little bit. Gumdrops, they just don't have the strength.
Exactly. I was thinking we could use something a little more sturdy, maybe like some cardboard.
Oh, yeah, and it doesn't move at all. We can totally make this, we'll max this out. I'll just put this over here. Okay, fair
right.
enough. Okay. if you want to build a block tower, you might think the fastest way to do it is just by building a single stack of blocks. But science may have a few things to say about that, and those things would be no. Let's try it with books.
The books are much wider than the blocks, so that will give me a wider base, right? But it's all about the center of mass. You compare how wide it is to how tall it is.
Right now, it's pretty wide and it's not that tall, so the center of mass might be around here.
But if you go high enough, how high it is compared to how wide it is changes a lot. It's getting higher, but not any wider.
The center of mass is probably right around there somewhere, which means it's gonna be really hard to balance that. Whoa, careful, almost. I can do a little bit more, I bet. Oh, careful, careful. Whoa. It'll only get so tall. So there you go. You can never stack a single stack of anything very high. But just in case you don't believe me, let's max it out. Ah, ha, ha. Oh, careful. Now it's time to see how high, whoa, how high I can make a single stack of boxes. Okay, and whoa, 6 boxes! 6 boxes! 6 boxes! Whoa! Can he go as high as 12? Let us find out if I can go as high. Apparently not. Can he go as high as 11? Can he go as high as 11 boxes? Let's find out. Oh, careful, careful, careful. And, ha-ha, a single stack of boxes! Huh. Okay, well, like I said, you can't stack a single stack of things too high, because it will fall. Ha-ha. Science! 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 This is a pencil. You probably have one of these at home and use it for all kinds of interesting things like writing and drawing, and that may be it. But if you have a lot of pencils, you can build stuff. I'll show you some of my favorite pencil builds. Check this out. It's a pencil cube.
If you want to try building one yourself, you build it like this. Get a piece of foam and then lay out 11 pencils this way, and then another 11 that way, so they make a nice square. Then take sharpened pencils and stick them into the foam in all the gaps. Go all the way around, and then keep adding more layers of pencils, and eventually you will have a cube. Now, if you don't have 366 pencils at home, you can do the same thing with toothpicks.
Now, if you want to research this on your own to find the instructions, just try looking up pencil cube. Okay, that's not the only thing we can build with pencils. Check this out, a pencil asterisk. Phil, can you max it out and add some more pencils? Yeah, so I did. I maxed it out with even more pencils. And then I thought, well, could I max it out again? So I did. This is what it looks like with even more pencils. And in fact, I removed the inside pencils and the whole thing still stays together. And then of course, this is the maximum number of pencils you can do with this configuration, because as you can see, it starts to become a sphere and you kind of run out of pencil length. There you go, maxed out pencil structures. Of course, I've used all of my pencils, but that's okay, I will buy some more. I will just write myself a note to buy more. Actually, there are sharpened pencils on the bottom of my pencil cube, so I'll just write this note with the pencil cube. What could possibly go wrong? Okay, ready? 1, 2, 3. And it's still standing! Oh, that one's not sharpened. Oh, here we go. Where'd my book go? Ooh, look at...
Sarah and I have maxed out a geodesic dome out of gumdrops, oranges, watermelons, and more gumdrops. But now we're making one using glue and cardboard circles.
Are those the same distance?
After a bunch of time assembling and gluing, we have a giant maxed out dome.
Okay. There? Are we done?
I think so.
We're done?
Yeah.
Yeah! Max out dome. How
how many points do we have?
So many.
Do you think we can lift it?
I think
I think
so,
that's the
yeah.
top. Try it.
See.
Okay, whoa. Whoa! Wait, we can spin it.
It was really light and also really strong. Strong enough to hold upside down.
As a fruit bowl, it'd be pretty good. This is so strong. I'm surprised at how strong this structure is.
There you go, Science Max, experiments at large, geodesic dome. And now it's sort of a geodesic disco ball.
I like it.
Whoa, whoa, whoa,
Okay, careful. Careful, careful. All right, putting it down, putting it down.